Alright, we're going to go ahead and look at numbers 8 and 9 now. Number 8 says there is wall 8 foot tall, 1 foot from the side of a building. What is the shortest ladder that can reach the building over the wall? Okay, so let's look at this picture. I've got my ladder here. It's H long. It touches the top of an 8-foot fence, or an 8-foot wall. And then there's this building that goes up higher that it has to touch, and there's 1 foot in between. So what I did is set up a proportion that gave me a connection between h, the length of this, and this value here, which I called x. So my big hypotenuse here is h. My little hypotenuse from here to here, well, that's the square root of a squared plus b squared, or in this case 8 squared plus x squared. So I have this piece here. So I've got hypotenuse, big hypotenuse to little hypotenuse, and then I've got big leg to little leg. Here I've got my big leg is x plus 1, my little leg is x. And then of course to solve for h I can just multiply by this. So I'm here. And then when I take the derivative, I get this bit here, and I want to optimize, so I'm setting it equal to 0. So I just want the denominator to not be 0 and the numerator to be 0. So if I take 4 cubed, that gives me 64. So 64 minus 64, so I want x to be 4. So when x is 4, then I need to say, okay, what is my h? Well, I can plug that back in here. So I get 4 plus 1, get all that, and I get 5 root 5. Okay, so let's give that a look. So here's my equation. You can see that here I dip down at 4. I get my lowest height available. Hopefully that should be 5 root 5. And we can see 5 root 5 goes right through there. Okay, and then let's kind of get a look at what that means in this situation. So basically I've got this ladder. This green thing is my ladder. It has to always go through this 8-foot point here, and the building is 1 foot away. So as I move through this, you can see it always touches 8 foot. This ladder, to go all the way to touch here, has to be really long, obviously. But so we can of course see that there's going to be some point, whoops, along here. They're getting longer, getting shorter. And so I want to find where that length is the shortest. Okay, so this length is calculated here. I have this value is this length. It's the length here, that's my y value right there, and then my x value as well. So I've found this hypotenuse of this triangle, and then I'm measuring it here, so you can see as I move this, oops, sorry, I want that to be 1. Alright, as I move this, that value goes down, and then it starts going back up at some point. And what that point is, well, of course that point is my 5 root 5. Oops, I did that again. Okay, it's my 5 root 5, so it goes down to the 5 root 5, and then starts getting longer again. Okay, so that's that problem. Number 9 is a very similar problem. In number 9, we want to find the equation of a line that goes through 3, 4, and that makes a triangle with the coordinate axes to make a minimum area. So what I'm looking at is I've got this line, it goes through 3, 4, and I want to make this area inside here to be the smallest I can. So, well, I know that the area of a triangle is 1/2 base times the height, and I know that the equation of this line, well, it goes through 3, 4. I just don't know what the slope is. I'm trying to figure out what the best slope is. So I called that A. My slope B. Maybe I could have called it M, but I called it A. Anyway, so now I can base the height. I know that the height of this is always when x is equal to 0. So if I put in x equals 0, I figure out what my height is, and it's here. I know that my base is whatever this line is when y is equal to 0. So I find that here. And now I can rewrite big A, area, in terms of little a, my slope. And then I'll simplify that to 12 minus 8 over A minus 9/2 A. Okay, and just like normal, I want to optimize, so I'm taking the derivative, setting it equal to 0. I took the derivative, and I find, so here, once I solve this, since I'm taking the square root, I would have positive and negative, but you can see I'm going to have my negative slope in this situation. So I have the negative 4/3. And then, of course, I just put that in because it asks for the equation. It says find the equation of the line. So I found the equation of the line right here, and we can explore that a little bit. So I have this point. You can see 3, 4. Everything has to go through 3, 4. But my A can change, right? It can go from here. And as my A changes, the area inside, of course, is going to change. Okay. So this value here represents the area. So you can see that at some point it gets smaller, but then starts getting bigger again. This is the line that I found for my smallest area. You can see I'm going to approach that, touch it, and then start going back. So at that point, what that area is, I want to find the slope during that, and that's what we did here with the negative 4/3. And if we zoomed in, we could get a sense of that being negative 4/3. Our A is slightly off there. There you go. So we can see that better. And we could see that our lines match up. Okay, so that gives us 8 and 9, and then the next video we'll finish up